Hello everyone, and welcome back to the channel. Have you ever wondered how the sound of my voice is reaching your ears right now? Or how you can hear a dog barking down the street, or the beautiful melody of your favorite song? It all comes down to one of the most fundamental, yet fascinating, phenomena in physics: sound waves. So today, we're going on an auditory adventure to uncover the secrets of how sound travels. Get ready to have your minds blown, and maybe your ears too, but not literally, I promise. So, what exactly is sound? At its very core, sound is a vibration. It's a type of energy that's created when something moves back and forth or vibrates. Think about clapping your hands. When you bring your hands together, they vibrate for a split second. This vibration disturbs the air particles around them, setting off a chain reaction. It's like a domino effect, but with invisible air molecules. One particle bumps into the next, which bumps into the next, and so on. This disturbance, this wave of energy, is what we perceive as sound. To really get this, let's picture a calm, still pond. Now, imagine dropping a small pebble into the center. What happens? You see ripples spreading out from where the pebble landed, right? Those ripples are waves traveling through the water. Sound waves work in a very similar way. The source of the sound, like my clapping hands, is the pebble. The air around us is the pond. The vibration from the clap creates waves that travel through the air, just like the ripples in the water. These waves are called longitudinal waves, which is a fancy way of saying the particles of the medium vibrate parallel to the direction the wave is moving. They get squeezed together in some places, called compressions, and spread apart in others, called rarefactions. It's this continuous pattern of compression and rarefaction that carries the sound energy from the source to your ears. Now, a crucial point here is that sound needs something to travel through. It needs a medium. This medium can be a gas, like the air we breathe, a liquid, like water, or a solid, like a wall or the ground. Without a medium, there's no sound. This is why in space, which is a near-perfect vacuum, it's completely silent. No matter how big an explosion is in a sci-fi movie, in reality, you wouldn't hear a thing because there are no particles to carry the vibration. It's the ultimate silent treatment. So, the next time you see a spaceship battle with huge explosions and loud laser sounds, just remember, that's pure movie magic. Let's talk about the speed of sound. It's fast, but not nearly as fast as light. That's why you see lightning before you hear the thunder. The light from the lightning bolt reaches you almost instantly, while the sound wave, the thunder, takes a little longer to travel the distance. The speed of sound isn't constant, though. It changes depending on the medium it's traveling through. Specifically, it depends on the density of the medium. Think about it this way: in a solid, the particles are packed together very tightly. So when one particle vibrates, it immediately bumps into its neighbor, and the energy is transferred very quickly. In a liquid, the particles are a bit more spread out, so the transfer is a little slower. And in a gas, like air, the particles are much farther apart, so it takes even longer for the vibration to travel from one to the next. This means sound travels fastest through solids, slower through liquids, and slowest through gases. For example, in air at room temperature, sound travels at about 343 meters per second, or about 767 miles per hour. But in water, it zips along at nearly 1,500 meters per second. And in steel, it's an incredible 5,960 meters per second. That's why you can hear a train coming by putting your ear to the track long before you can hear it through the air. The solid steel rail is a much more efficient highway for sound than the air is. Temperature and pressure also play a role. Generally, sound travels faster in warmer air because the molecules have more energy and move around more quickly, helping to pass the vibration along faster. So, the sound wave has been created, it's traveled through a medium, and now it's reached its destination, your ear. But how does your ear turn this vibration into something your brain can understand? This is where our own biological equipment comes into play, and it's absolutely brilliant. The journey starts with your outer ear, the part you can see. Its funnel-like shape is perfectly designed to collect sound waves and channel them into the ear canal. At the end of the ear canal is a thin piece of skin stretched tight like a drum, called the eardrum. When the incoming sound waves, those compressions and rarefactions we talked about, hit the eardrum, they make it vibrate. It's just like hitting a real drum. This vibration is then transferred to three tiny bones in your middle ear. These are the smallest bones in your entire body, the malleus, incus, and stapes, also known as the hammer, anvil, and stirrup because of their shapes. These little bones act as a mechanical amplifier. They take the vibration from the large eardrum and concentrate it onto a much smaller area, the oval window, which is the entrance to the inner ear. This amplification is crucial, especially for hearing faint sounds. Now we enter the inner ear, and this is where the real magic happens. The vibration passes through the oval window into a spiral-shaped, fluid-filled structure called the cochlea. It looks like a tiny snail shell. The cochlea is lined with thousands of microscopic hair cells. Yes, you have hair inside your ears, but not the kind you can style. As the fluid inside the cochlea vibrates, it moves these tiny hair cells. Each hair cell is tuned to a specific frequency, or pitch, of sound. High-pitched sounds move the hair cells near the entrance of the cochlea, while low-pitched sounds travel further in and move the hair cells at the very tip of the spiral. When these hair cells bend and move, they generate electrical signals. These signals are then sent up the auditory nerve directly to the brain. Your brain receives these electrical impulses and interprets them. It deciphers the pitch based on which hair cells were activated, the loudness based on how many cells were activated, and how much they moved, and the timing to figure out where the sound came from. It puts all this information together in a split second, allowing you to recognize my voice, enjoy music, or react to a warning siren. It's an incredibly complex process that happens so fast and so effortlessly that we completely take it for granted. From a simple vibration in the air to a complex electrical signal in your brain, the journey of sound is truly remarkable. So let's quickly recap. Sound is a vibration. It needs a medium, a solid, liquid, or gas to travel through as a wave of compressions and rarefactions. It travels at different speeds depending on the density and temperature of that medium, fastest in solids and slowest in gases. Finally, our amazing ears capture these vibrations, amplify them, and convert them into electrical signals that our brain interprets as the rich and varied world of sound we experience every single day. The world around us is constantly buzzing, humming, and speaking, all thanks to these invisible waves of energy. I hope this journey into the science of sound has been as fascinating for you as it is for me. Next time you hear a bird sing or a car horn honk, take a moment to appreciate the incredible physics and biology at play. It's a reminder that there's amazing science happening all around us, all the time. Thank you so much for watching today. If you enjoyed this video and learned something new, please give it a thumbs up. And don't forget to subscribe and hit that notification bell so you don't miss our next adventure into the world of science. Let me know in the comments what you found most interesting, or if there's another topic you'd like me to explore. Until next time, keep asking questions and stay curious. Bye.